Thank you for the introduction and thank you for the invitation to speak with you, Camila. It's a pleasure to be back after 2 years of postdoc. So, I will talk to you about my recent talk with Emmanuel Brouillard, who's professor at Ortober, concerning limit theorems on nilpotent groups. So, really, this kind of topic belongs to a more general subject. We consider G to be a big group. A probability measure on G, and you take some random variables distributed according to mu, so x1, x2, etc., xn. You multiply those variables. So, and you are interested in the distribution of this new random variable that is the n-fold convolution. Here, it says identically distributed independence of your mu. You want to understand the distribution of the internal product. So we look at the law of this product, and it is the n-fold convolution power of the. So the question I will try to answer properly in this book is what does mu mean? So here I do not specify that G is nilpotent. I ask the question in general, and it really makes sense in general. For instance, you can ask about the case where G is a compact group. So in this case, an interesting question is, does mu distribute at a certain rate toward the Haar measure of G? You can ask the question when G is a semi-simple group, and then, for instance, it's SLDR, and then you can ask about what's the norm of the product, a random product of matrices, or what are the directions of the singular vectors, or you have many questions that gives a sense to this question. And today I will focus on the case where G is nilpotent. So for the whole talk, we work under the following assumptions. So the first assumption, G is nilpotent and simply connected. Simply connected with is connected its own point. And nilpotent. So for instance, it's exactly the same as saying that G is the same is RD, the vector space RD, but endowed with the structure of algebraic group. A structure of a group that is polynomial. So the composition law is polynomial and the inverse is polynomial. It's also the same as saying that G is a connected subgroup of the standard unipotent group, which is given by the matrices with words on the diagonal. And we got a triangle. This project UD, and you ask that G is a connected subgroup of that. That's another way of saying this assumption, but maybe I should have also started with the definition, which is just say that the central series of G terminates in a finite number of steps to 0, and G connected with the here, the same equivalent. G. This standard. Second assumption. We are going to assume that mu is not too degenerate. So suppose that the support of mu is compact. So this is quite another thing, but I don't want to enter into complications if I specify weaker moment conditions. And also we assume that the support of mu is not included in a proper subgroup of G, nor any translates of a proper subgroup. And not included in some image where G belongs to the group and H is the focus. For instance, imagine that I don't know, G is just R, the real line. The second condition means that G is not included in a lattice, so in Z or during R times Z, and nor any translate after this. And the second condition is called periodicity condition. The first condition is just the moment. Is there any questions in this condition?
So for example, if you're on R, you take something which is weight on 1 and square root of 2. That's okay.
Yeah.
So H a proper Lie subgroup.
Yeah, proper. Yeah.
Or closed
Yeah,
subgroup.
close.
Okay, fine.
Okay. Any other questions? Okay, so examples. So the first example that comes to mind, and for which I will be very fast, is the case of the real line. So J equal to R with the edge. So in this case, what we have, we know that classical probability theory tells you that if you look at x1 plus xn, then it's distributed around the average, which is n times the expectation of the average of u. And around that, you have some Gaussian distribution, which is spread around the average scale square root of n. And of course, if it's spread the scale square root of n, then the height is also a scale square root. So 1 over 2. So this is the picture that you can have in mind in the classical case where G is just R with the addition. So the spread around the average is square root of n. Now let's look at the Heisenberg case. So the case of the Heisenberg. So this means that G is equal to, let's say, R2 plus R with some specific group structure, which is not the typical, the usual group structure on R3, it's something else that is not permitted, where the group structure is defined as follows. So we take two elements in V. So Vs and WT. We want to multiply them. So V is the coordinate in R2, S is the coordinate in R, and same for WT. So how do you define the product? And just take the sum plus V plus W, S plus T. And then he adds some linear terms, alternate linear terms into V and W in the third coordinate. So here I will take the wedge product. So V wedge W. And this means this is the usual coordinate for the wedge product. So it's just Vx WY minus Vy WX. So you can check that this defines a group structure on R3 that is not limitative, it's actually nilpotent of nilpotent plus 2. And so question, what does x1 times xn looks like in this setting? So you can write x5 as vi x I, and then you look at x1 and xn. So let's compute this product. It's the sum of the di's, the sum of the si's, plus some term that takes into account this new linear form, that is not an addition. So it's the sum for I less than k, of the I which we j. So these are two standard inputs. Which you understand by classical probability theorem, it's not always so. And there is this new term that we need to understand. New term T. So question, what does Tn look like? What's the amplitude of Tn and what scale does it do? Is there any question on this formula? So what is the amplitude? So here we have two cases to look at. First case, suppose that the expectation of the n is equal to 0. So this is the sample case. Another way to say it is that the expectation of mu projected to the abelianization of G is equal to 0. So in the central case, the way to understand the amplitude of Tn is just to look at the expectation of Tn squared. So let's compute it. The expectation of Tn squared is the expectation of the sum for I less than J, K less than A, from the expectation the I which K times K which even. But here what you notice is that if one of the variables, one of the four variables in this expectation appears only once, then this expectation has to vanish because of the not a zero expectation. So the only terms that you get are those for which K is equal to I and A is equal to J. So this is 0. I J is different from K. So what you get is a sum for I less than K, and the expectation in this way. The I J. So these are positive terms. You have roughly n squared positive terms, so the order is the amplitude of Tn squared is n squared. And so what the heuristic I want to give you is that the amplitude of Tn is n. This is some random variable that is spread at scale n around the expectation which is this. So here we have n squared. Let's say n around its average, which is 0. Is there any question on this? So I do not give a formal intuitive meaning to this. I will come later to that. But what I want to say is that here in this example, you are squared, let's say square root of n around the average. And you can see here you have the same behavior, but it's not square root of n, it's n. Okay, so second case, the non-trivial case. The expectation of n is equal to some mu, which is not 0. So in this case, we can understand Tn by dividing it into two terms. One term that corresponds to the sample case that we just studied, and some new term. So write Vi as Vi prime plus E, where Vi prime is simple. Now you have that Tn is the sum of the wedge of the Vi's. But if you use the linearity of the wedge, we can get some Vi prime. So it becomes the sum for I less than j of Vi prime for which is j prime plus the terms that use the p. So it's the sum from I between 1 and n of n minus 1 of EU, which here I just use the linearity of the wedge. You can check that this formula is correct. And now I want to understand the amplitude of this term Tn. So you see that you have two terms that play a part. And this term we have just studied because it corresponds to the Tn for some centered group. So the same is n. And these are the terms. Well, what is it? It's some sum of n terms which are all independent. The Vi primes are mutually independent. You have a coefficient which is roughly over n. And you know that the sum without coefficient of centered random variables is of order square root of j. So the total is n to the 3 over 2. So we have to make a guess, we will understand. We would say that Tn leaves the scale n to the 3 over 2 around its average, which is 0. So the conclusion of this analysis in the Heisenberg case is that depending on whether the work is centered or not, the work spreads at a certain rate on its average. The rate of spreading of mu n. Depends on the expectation of mu in the Abelinization. Is there any question on this example or the conclusion? So this is all heuristic. I'm not giving any formal statements. This formal statement will come. Okay, so now we have some examples that help us understand what could be the general case. So what is the geometry of mu now? For arbitrary multiple group. So for the general case, we are going to identify the group, which is some abstract object. Yes, some Lie group, abstract nilpotent group. And we are going to identify the vector space through the exponential map. So we identify the group to its Lie algebra. So this is equal we recall that G is simply connected nilpotent group. And I'm going to call G vertex the Lie algebra. Okay. So the time space is there. And this is the fact, the theory of nilpotent groups, that the exponential map. The map that goes from the algebra to the group is the different. So this different allows you to take the group structure G and push it back into some group structure on the algebra. And from now on, I will just look at the algebra and this group structure on the algebra. So now, starting now, we identify G with the algebra of the group using this exponential map. So in particular, you have a group structure. So now I'm in a case where I have a vector space and also a group structure on the vector space. So I can use also the theory of vector spaces, the notion of direct sum decomposition, subspace, etc. There is some well-defined notion of direction in the group. And so the goal of the next thing I'm going to explain is to say the following. There exists a direct sum decomposition of a vector space. We can write G as a sum of the ends for the finite numbers in the 1 and 2. Thank you. So it's not a direct sum of Lie algebras, it's a direct sum of vector spaces. Vector spaces. And such that you project mu n to the p components of the direct sum decomposition. Then mu n has leaves the scale into the p over 2 around the other. For all the projection, so it's projection onto ME of mu n. So it is spread let's say n to the p of 2 around 7. So this corresponds to what we observe in the Heisenberg case. In the Heisenberg case, you had R2 plus R3, And you have a decomposition R3 is equal to M1 plus M2 plus M3, where M1 is always the upper component, and M2 and M3 depend on the center of the space. So, for instance, if the root is centered, then M2 is the R component. We get 0 for M2, and we need centered. And in the non-centered case, M2 was 0, and M3 was 1. Pardon. And how do you define this decomposition for general nilpotent algebra? So, the general case. So first, you have to introduce some decreasing sequence of ideals. So it's given by the formula by induction. So you set G0 equal to G1 equal to G. You have the first two steps of the induction. And then if you want the I plus 2 step, E after 2 is equal to the sum of two subspaces. First is just G bracket G I plus 1. So if I do continue the definition and stop here, I just get the descending central series. But actually I have some other term, which is expectation of U in the adenization. So give me the sequence G, G1 equal to G, contains G2, contains G3. You have to stop at some point. So if you look at this formula, you can look at first what are the first elements of the included sequence. G2 is first actually divided into. D3 is what? Is expectations. I call this EU. It's just EU E plus the third element of the dynamic central series, D brackets D bracket G. So in a way, it's the same as the descending central series, but the expectation of U contributes with weight 2 instead of weight 1. So well, this is some decreasing sequence of ideals, and the feeling behind that is that it represents the zone of the algebra for which the rate of spreading will be faster than n to the I over 2 for GI. So, here, GI is where anyway spread and rate faster than n to the I over 2. And so if I want exactly the domain of the space where it spreads a scale n to the other 2, exactly this scale, so I can renormalize exactly by this concept, then I will look at just the complementary subspace between GI and GI plus 3.
Okay. Yeah, I don't understand. P mu, it's a number or it's a.
No, it's a vector.
Yes.
So this is defined in the in the abelianization of the group.
Yeah.
But actually, if you take any representative in the group, in the algebra, this is going to give you the same notion of decreasing different ideals. So there is a slight abuse of notation here. But, it's
So in the examples, these works here for b bigger than 1 were all with average 0.
what? Sorry.
In the examples, they're always centered around 0,
Yeah.
the t-nth.
Yeah, in this example, yes.
That's not true in general.
No, I don't think so. I think if you go to a state 3 nilpotent group, you have some. We'll try to come to that. So now I introduce, I give you, I'm going to give you the local limit theorem and further renormalization. So after this point of view, we want to define the following normalization. Define combination for R equal to D. We define dr. So it's on the Marquisian of the algebra of the vector space G. That is the sum for I to the 1 and Q of R to the I over 2 identity. So you have the direction decomposition. On each subspace of this decomposition, you act diagonally with like an homotety with weight R to the I over 2. No, R to the I. R to the I. So, right. Well, no different technology. We said it. We have it. So for each I, choose mi, the complement of the place, that's gi with mi plus gi plus 1. So this is exactly where the work has scaled n to the I over 2. So now you define the correct renormalization. Now for R, positive, then the R to be the same as the identity. And R to the I. And equal d mu, the determinant of the exponent that appears in the determinant of the R. So it's a positive number given by characterized by the formula. Determinant of dr is R to the d mu. So it's just some number, and the bigger it is, the more spread the work becomes. We in my development model, we call it the homogeneous dimension of the work. So now, here, is the local limit. It goes as follows. There exists a smooth probability measure that I call mu. It's a probability measure mu. Such that for all continuous function on G with compact support, one has the following estimation. You're interested in mu n of f. So describing mu n is a way to say I know what mu n of f is, and I'm telling you that actually it's really close to the following. So I start with mu, I dilate it using d square root of n. If you push forward by the dilation, then I translate everything using the expectation of the work. I apply this to the test function. And then, so this is not really an equality, there is some error term that we can control. And it's integral, depending on mu and n, of n to the minus c. So this is the first conclusion. But also what is interesting is that this error term is uniform when you replace f by some deviation by a translate of arbitrary elements. So moreover, is uniform. If one replaces f by some deviation, so f composed with right multiplication by g, or composed by left multiplication or NG. If this error term appears a bit mysterious, just imagine that it's negligible compared to the first term, as long as the deviations here are not too wide. Also, it's sort of answers to the original question with which I started the talk, because if you want to understand UN, what do you do? Well, you take this probability measure mu, you dilate, you translate, and you got a good approximation of UN. That's the philosophy of the statement. Yes.
Vitolo is what depends on the superfet on the side of the board.
Yes. Yes. So you can say that little o depends on f as the L1 norm of f, and the supremum norm when the Fourier transform of f has compact support, and then it also depends on the R and on this compact support, and then using explicitly the dependence on f in this case where f hat has compact support, you can get this. We do not. Yeah, we not explicitly stated on what it depends in this case for when f is continuous. No. It needs to depend on the variation of it, not only the supplement. Okay. Is there any other question? So you see, I only made informal explanations of Bénard, but this is formal statement, and it corresponds to what I said earlier. So the first question was what does mu look like? Now it goes down to the next question, what does mu look like? I have it 45, right?
Yes. 4 minutes.
So one nice thing about mu is that it is unique up to choosing the subspaces and I that I chose earlier. So as the local limit theorem implies the central limit theorem, mu must be unique. Modulo the choice of the decomposition. Modulo the choice of the endpoint. And so what I want to say when I say that local limit theorem implies central limit theorem, I just want to say that if you want to know what mu is, you take mu(n), you recenter everything by minus n exclusion, and then you take a step back, dilating in reverse way, and mu is going to cover. So d1 over sum of n, mu(n) times recentering. This convergence, so in terms of probability, Weak-Star convergence. So mu is unique because it's only expressed in terms of these events only depend on mu and the choice of the elements. What can you say about mu? For instance, we can also characterize when mu is a Gaussian distribution on the vector space. It makes sense to say when it's mu Gaussian. And for instance, mu is a Euclidean Gaussian. Even only if for one time, one has that mu bracket I is equal to G I plus 1. So this G bracket I is the item in the descending central set, not the decreasing sequence idea I talked earlier. No, that's just the standard decreasing address. You have this criteria. When you get, if you give me some explicit nilpotent the algebra, you can ask, does it satisfy this? It's not too hard to compute for low-step algebra. Characterization of point being solution. So to conclude, I'd like to mention something a bit odd that we noticed with Emmanuel while working on this project. It's about the support of the limit distribution. So write mu as mu of x dx, where dx is the leg and g, and u is some non-negative smooth function. So in the center case, it is known that u never vanishes, and actually you have some Gaussian estimates, a Gaussian lower down and a Gaussian upper down for you. They exist. So if we denote by normal bits the distance to 0 for a left environmental, then there is a matter that u for this is less than e to the minus 1, e to the minus alpha normal square, and more than alpha, e to the minus alpha normal square. So you have disclosure estimate. In the non-centered case, it is possible that you vanishes, so it's not, so it only vanishes in the proper closed set. Fact. If Fg is the free algebra of set 3, Fg is free, it's a step of set at least 3. Then for any distribution mu driving the work that is non-centered, the limiting measure that we get in the central limit theorem is properly supported by the space. And I'm going to stop. Then for all mu non-centered, one has that's the support of mu supports the limiting measure mu and it depends on
And on the line, new.
Not so much. If you change your limit, you have some diffeomorphism of G that sends mu to the other, and you know the diffeomorphism. So yes, it does depend on the MI. Not really. Yes.
Do you have applications to say some boundary or
Yes. So we have two applications of the limit theorem. The first one was to recover a result of the Barch concerning the boundary of nilpotent levels. So under the assumptions that I stated, and either we just need a moment condition of order 2 plus epsilon. We get the triviality of the Poisson boundary on interconnected nilpotent levels. Diverged for just the positive number. So it's not new, but it's a new proof. And something new that we got is not about the Poisson boundary, it's about the eco-distribution of nilpotent random walks in a homogeneous space. You take a finite volume homogeneous space, so it's G over lambda. You take a random walk on this homogeneous space obtained by taking a unipotent subgroup of G, and you take mu probability measure in this unipotent subgroup, and then this unipotent subgroup acts on the homogeneous space, and so you have a way to walk randomly on this homogeneous space within this probability measure on the unipotent part. And we show that for any starting point, mu n delta x, so the n step distribution of this walk is going to eco-distribute towards some homogeneous subspace. So it's eco-distributes in Caesar average when the walk is not centered, and that's optimal because there are counter examples that tells you that the Caesar average is necessary. And when the walk is centered, then you have the eco-distribution in the system. And so that's another application.
And for the measures which do not have some second moment, can one have a version, for example, for central limit theorem, something with the domain of the affection of stable law, or can one expect?
Yes, I think there is work on that by Laurence Alofcost, Céline Jong, and other people. They wrote a book about that, I think. I'm not a specialist
But
in
we
this
don't
case.
know in general now.
So-
It's,
What?
I think we don't know in general.
Okay. Yes.
Some more general than your result.
Yes.
Without second comment.
So there are some unique cases when if you know exactly how the measure mu is distributed, meaning that you have an asymptotic for the Z probabilities, and it's a good asymptotic, then there is a way to find another normalization converges. Can see good sense to the theorem. Yeah, no, I don't. I should work on that to answer better your question. Yes.
My other question just about good moment conditions like in your results. So you mentioned these constants, these not standard constant polynomial constants like 5 over 2 or something. So given an important group, you have finitely many possibilities, right? For what constants can arise for
exactly.
And these possibilities for this polynomial term, are they related to this support you mentioned? So you have mentioned that possible support of your.
Okay. So are you asking, does the mu here tell you about the support?
Rather, if support can, if you know the support, do you know the constant?
No, I don't think so. No. Because there are cases. So these cases with non-full support are rare still. So you have in the central case, you always have full support.
But in the centered case, you always have the same constant, right?
But there are non-centered examples with full support, and they have a different limit. So in the Heisenberg case, right, you always have full support, centered or non-centered, but you have different limits.
And two, when you say that you characterize indicator Euclidean Gaussian, when you don't have a Gaussian, is it you still have a stable law, or do you have something that is completely different?
I think you have something that's completely. Just look at the centered case, the centered Heisenberg case. You know the distribution. So the table is the model stable for plus, right? So it's going to be stable for multiplication, but not plus, right? I think. So what you get so you look at R3. What is the mu in the central case? Mu center. So in this case, mu is the low time one. So it's B1, B2. So these are two independent bonding motion on R. And then you have some third coordinate, which is called the Levy area. That's given by the Brownian path. Sorry, B1. 2B1 for independent, B1, B1. And you look at it's called the Levy area for the Brownian path until time 1, and given by these two guys here. So you have some Brownian path, and it's supposed to be something like the area that's here. When you go from the start to the end. So there is you need to give a meaning to that, because I guess it's going to be some integration of the Brownian path, so one dimension, one differential form. And so you have a characterization of this mu. So I don't think it's stable. It's a diffusion process.
And it's well understood. Its moments are known, for example.
Sorry?
Its moments are known.
Yeah, yeah, you have exponential decay, you have something like that. You have this lower down and upper down. So in our theorem, new it's completely explicit in terms of diffusion process. That's a good language to put it in. And it's diffusion process on a group for some left invariant remaining metric. So it's not the addition that you want to consider. It's the multiplication. So it's stable. Mu is stable in the sense that if you do mu convoluted to this mu, and then go normalized by d then it's the same as mu. In this sense, it's stable.
And I had one last question, which is there any way of defining a random walk on a Lie algebra directly? Because it seems that what you write here only depends on the associated gradient of the group. So only on one term of the Baker-Campbell-Hausdorff formula. So maybe it's possible to define something directly at the language of Lie algebras.
One term of the Baker-Campbell.
It seems so that you look at something finer than the
Okay.
grading.
Yes, exactly.
So if there are higher order terms, they don't matter.
So you're right. You can say that you know the dependence of mu is only what happens in the abelianization. So the first two moments of mu in the abelianization, and the first moment of mu in what is just after the abelianization. So that's what you're saying, I guess. And you're asking, is it possible to define directly
A random walk on a Lie algebra.
on any Lie algebra?
A nilpotent, yes, for example. Finite dimensional nilpotent.
So I'm not sure I understand the question because nilpotent algebra is the same as simply connected.
Yeah, well, just write a formula that uses plus and Lie brackets instead of writing star, and hopefully get something simpler.
Ah, okay. So you go deeper and deeper and you see. So what so you want to use just the first two order terms, you said?
Hopefully, yes.
So you take x and y in the algebra. Okay. And you want to say
It was a vague question, like, is there a way of defining a random process?
what?
Some random walk on a Lie algebra that only uses
Yeah.
the plus and a Lie bracket.
So
Maybe have a
yes.
longer time for discussion of the
okay.
second topic.
Yes, sorry,
Yes.
sorry.
Let's.
Thank you again.
But we have maybe 1 minute break until next topic.